Hello and welcome. Ever stop to think about what happens when the tiniest particles in the universe crash into each other? It's not some simple cosmic game of pool. Nope. It's this fuzzy, weird, probabilistic dance, and it's all run by the strange rules of quantum mechanics. Today, we're going to pull back the curtain on one of the most fundamental ideas in all of physics, quantum scattering.
So that brings us to the big question, right? If you can't even know exactly where a particle is, or exactly where it's headed, how on earth are you supposed to predict what happens when it collides with something? It sounds totally impossible. But physicists have this stunningly elegant way to figure it out. Okay, let's dive into this.
All right, so first things first, let's set the scene. I want you to imagine a single particle, just a lone traveler on a quantum journey. We can actually map out its whole adventure in 3 basic stages. What's so cool about this is how it frames the entire problem. Way back in the remote past, our little particle is just doing its thing, moving along predictably. Then, bam! It hits the interaction zone, where some kind of force starts pushing and pulling on it, and finally, in the far future, it comes out the other side, scattered, changed. The whole goal for a physicist is to connect that beginning to that end.
So how do they do that? Well, they don't try to track the particle's every little move. No, that will be impossible. Instead, they pour all their effort into calculating one single, almost magical number that holds the key to the whole thing.
And that number? It has a name. It's called the scattering amplitude. You can think of it as the ultimate cheat sheet for a quantum collision. It's this special kind of number that, once you've got it, lets you figure out the odds, the probability of that particle scattering off in any possible direction. It's everything.
And that right there, that's the whole point. If you can solve for the scattering amplitude, you can predict the statistical future of that particle. You've cracked the entire problem. So, the million-dollar question is, how do you get it?
Well, you knew there was a catch, right? With anything quantum, it's never quite that easy. Turns out, calculating this number directly, well, the equation you have to solve is, it's a bit of a beast.
Yeah? There's a problem. A really, really big one. The direct path to the answer is basically blocked by this giant wall of mathematical complexity.
And here it is. Whoa. Now, don't panic. Don't worry about the symbols or the squiggly lines or what any of it means. Just take a second to appreciate that this thing, this equation that holds the key, is what's known as an integral equation. And they are legendarily hard to solve. It's a mathematical monster.
But physicists, they're clever. When you're faced with a monster you can't defeat in one go, you find another way. You figure out how to tame it, piece by piece. And they do this using a brilliant workaround, a kind of infinite series approximation. The logic here is just so simple and powerful. If the exact perfect answer is too hard to get, just start with a simple guess. And then you slowly add little corrections to it, getting closer and closer and closer to the real answer with every single step.
You know, it's kind of like trying to draw a perfect circle. You might start with a square, right? Then you'd snip the corners to make an octagon, then snip those corners, and you keep going. Each step gets you a little closer to a perfect circle. It's the same idea here. We start with a simple case, the particle doesn't interact at all, and then we add in the chance of 1 interaction, then 2, then 3, and on and on.
Okay, and this is where it just gets beautiful. Because when physicists started writing out this step-by-step solution, they found something incredible. The math wasn't just a bunch of corrections, it was telling a story. Let's see how that story actually unfolds in the math.
So, this equation you're seeing, that's the story, written out in the language of math. The total scattering result, S, is just the sum of all these different parts. S0 plus S1 plus S2, and it just keeps going. Each one of those terms is a different chapter in the particle's possible adventure.
So that first term, S0, is the simplest possibility of all. It represents the chance that the particle just misses. It flies right through the force field completely unaffected. So, chapter 1, nothing happens.
Now for the next term, S1, this tells a much more interesting story. This is the probability that the particle interacts with the potential exactly one time. It comes in, gets knocked aside, and flies off. Chapter 2, a single, clean hit.
And you can probably guess where this is going. S2 gets even wilder. This represents the chance of a double interaction. The particle comes in, scatters, travels a little bit, and then interacts with the potential a second time before flying away for good. It's like a cosmic double bounce.
And that is the grand reveal.
That terrifying, monstrous equation from before? It was never a monster. It was just a summary of all these possible stories, all added together. The story of a miss, the story of a single hit, a double hit, a triple hit, an infinite number of possible histories, each with its own probability. The math wasn't a monster, it was a storyteller.
So what's the big takeaway here? Well, for one, it shows us that even the most intimidating-looking math can be hiding a really simple, intuitive story inside. 2, it proves that approximation is one of the most powerful tools we have for solving impossible problems. And maybe most importantly, it reminds us that math isn't just a tool for calculating things. It's the language the universe uses to write its own stories.
It really makes you wonder, doesn't it? How many other deep secrets of the universe are just sitting there, hidden inside an equation, waiting for us to learn how to read the story it's telling? Just something to think about. Thanks for joining me.